So let's have a look at a more general way of doing multidimensional integration that doesn't rely on a statistical approach, relies on more analysis. So we're going to look at analytic integration to begin with in 2 dimensions, and we're going to consider a simple example, the integral of some function of x and y with respect to both x and y, the bounds of integration being x goes from a to b and y goes from c to d. So we're integrating this function over a rectangular domain. Analytically, the way in which we do this is we choose one direction to integrate in first. For example, here we'll do integrate in x first. Now, if we write big F of x as equal to the integral of f of x and y with respect to x, that's assuming that we can actually do this analytically, so let's write that as equal to that, then we can see that our original integral is equal to the integral of f of x and y, big F of x and y, evaluated between a and b, because we're now doing this proper integral here. This whole thing then is integrated with respect to y. And if we actually do this analytically, we can put in the value of b and the value of a into this expression, and we come up with, it's the integral of f of b and y minus f of a and y integrated with respect to y over the limits c and d. In this integration in x, in this bit up here, we have assumed y is, well, it's constant during the integration. We've treated it symbolically, we haven't allowed it to vary. So we've now found this integral here. We're just going to write that as the integral of g and y. So we're just going to replace this integrand here by g and y. It's just going to make it a little bit easier. We're never going to need this form again, by the way, so it doesn't matter that we've changed the nomenclature here. So this integrand g of y is just a function of y. So of course now we can integrate it in y. Now one thing to be aware of is this point here, and that is that in general our functions a and b, in general a and b might be functions of y. Okay, we're not going to worry about that for this example here, but in general that's possible. Making this whole thing a little bit concrete, again we're talking specifically about analytic integration here, let's integrate the function x squared y dx dy over the range x goes from 1 to 4 and y goes from minus 1 to 3. So let's just write this out. If we look at this inner integral here, the function is x squared y. We want to integrate x squared with respect to x, and that gives us x cubed on 3. The y here is still sitting there, it hasn't changed at all, but because we need to do this inner integral and evaluate it between 1 and 4, the bounds come in here, and if we plug those numbers in, it's quite easy to show that this thing becomes equal to the integral from minus 1 to 3 of 21y dy. Well, of course, we can now do this integral because this is just a function of y. And the integral of y is y squared on 2, and we need to evaluate it between minus 1 and 3, which is where these limits come in, and we can quite easily show that this integral is equal to 84. So we've integrated x first, then y, to come up with a single number. So in that example, as I already mentioned, y didn't change when we integrated with respect to x. We treated it symbolically inside the x integral. It's a bit difficult to treat something symbolically in a numerical case, because y doesn't really exist in a numerical example. The process for multiple variables, if we have more than 2, is pretty much the same. So quickly, if we have an integral with respect to x, y, z and t, and we're going to integrate it in that order, dx, dy, dz, dt, the inner integral direction might be chosen to be x. We keep y, z and t fixed and integrate with respect to x. We choose the next inner direction, in this case y, keep z and t fixed and integrate with respect to y. Choose the next inner direction, that's z in this case, keep t fixed and integrate with respect to z. And finally we do the outer integral and integrate with respect to t. So let's have a look at a graphical interpretation of what two-dimensional grid-based integration looks like. So a 2D integral can be viewed as calculating the volume underneath a two-dimensional surface. And so the surface height, z, is given by the function f of x and y. And so the integral is actually equal to the volume underneath this two-dimensional surface here. We can approximate the surface as a set of strips, each which has a width delta y. This is only an approximation, okay? So let's have a look at, we say, okay, the first strip, it's got a y value of y1. So let's say y1. Let's just say it's the left-hand side of the strip. And we're going to say we're not going to allow the function value to change on that strip. We know that strip's only an approximation to the surface, but it's maybe not too bad. So we're choosing the strips to be flat, and then we can calculate the area under the strip. So in other words, this two-dimensional area here is equal to the integral of f of x evaluated at y1. So f of x goes all the way from a to b, in this case it's 0 to 6, integrated with respect to x, and we get an area under this particular curve. We're going to call that g of y1. It's our x integral of our function with y set constant at y1. So we can calculate an area underneath this curve. Of course, we can estimate the volume under the entire strip as being the volume is equal to the width of the strip, which is delta y. So that width there is delta y, multiplied by the area of the strip, which was given by g of y1. So we can calculate the volume, and I think you can see we can split it into multiple strips and do exactly the same thing. So for strip 2, we choose a value of y, that's y2, somewhere across here. We assume that the strip doesn't vary across its width. We then calculate the area under that strip, the two-dimensional area, and it's approximately equal to the integral from a to b of f of x with y is equal to y2 integrated with respect to x. So we can calculate this thing using any method that we like. That's what we're going to define as g of y2, and of course the volume underneath that would be just g of y2 times delta y. For strip 3, we do the same thing. The area is approximately equal to that, where now the function's evaluated at y is equal to y3. That gives us g of y3, and so on. So we continue doing this process until we have a value of g for each value of yi that we choose to use. And this is what this looks like. So if we plot our function g of y, which is the two-dimensional area under that strip, as a function of y, we'll end up with some set of points that looks like those red points there. So g of y is represented at least approximately by the red dots. And we need to integrate this function then to estimate the volume underneath the surface. This bit here is performing the outer integral. So the volume under all the strips is approximately equal to the volume under the original surface. Now, we can see the way we've done it here, it's not necessarily a very good approximation. We've used a very simple approximation here. So, what we're basically saying is that our function, the integral of our function over x and y, can be written as an integral with respect to y of these functions, which in themselves are integrals with respect to x. And we can do that in the generic way by saying, okay, we have some set of coefficients here multiplied by these integrals, g of yj. It's just equal to this, the integral of x with respect to x. Now our simple strip model here has these coefficients, aj is just equal to dy. So we can then write our integral is equal to delta y multiplied by the sum of our integrals in x. So these things are our integrals in x. From a to b. So because we can't treat y symbolically, we can only use numbers in a numerical method. So let's go back and look at the two-dimensional example again. We're remembering now this is the 1D integral already calculated in x. The right-hand side is the outer integral. It's a 1D integral. Provided we know g, well, can we estimate this integral using techniques that we already know? Of course we can. It's a one-dimensional integral. So we can use Newton cotes, Gaussian quadrature, anything we like. So we'll have a look a little bit more detail in the next short video as to an algorithm to use to actually do this in practice.